Hi everybody, it's Professor Mitchell. Today we're starting chapter 4, which is probability. We are going to cover every part of this chapter except for the last section. We're not going to do simulations, but we are going to do all this other stuff. So not unusual when you're starting something new in math. It starts with a lot of vocabulary, and this is no exception. Okay. So let's start looking at basic concepts of probability. All right, so the objective of this section is to learn how to interpret probability values. So probability values range between 0 and 1. And what this is a number that expresses how likely something is to happen. How likely something is to happen. So if you see a number like 0.001, that means something that is pretty unlikely to happen, like 1 chance in 1,000. Okay. And then later on, we'll talk about odds and how they relate to probabilities. So any of you who like to go to Vegas or to the horse track, they usually express their probabilities in terms of odds. Okay. All right, so starting with the vocabulary, in probability we talk about events. You know, how likely is this event to happen? So an event is just any collection of results or outcomes. And I've got examples coming up here. A simple event is an outcome or an event that cannot be further broken down into simpler components. So let me just say, I am not used to this term simple event. I prefer the term outcome. So every so often you might hear me slip up and say outcome. When I say outcome, I'm talking about a simple event. Okay. And then you have the sample space for a procedure, and I'm used to calling a procedure an experiment. That consists of all possible simple events, all possible outcomes. So the sample space consists of all outcomes that cannot be broken down any further. Okay, so here are some examples of simple events and sample spaces. So this procedure or this experiment is you look at a single birth, and the birth is an example of an event would be one girl, okay? The sample space, which is all possible things that could happen, is either that single birth is a boy or that single birth is a girl, okay? However, if you look at 3 births, let's say we look at families that have 3 children, and we look at the order of, for example, in my family, it went girl, girl, boy. I'm the youngest, okay? But the other possibilities are right here. You could have 3 boys, you could have 2 boys and then a girl, you could have boy, girl, boy, girl, et cetera, et cetera, et cetera. Okay? So each of these things, these 1, 2, 3, 4, 5, 6, 7, 8 things, are what they call simple events. All right, these things cannot be broken down any further when you're looking at the experiment being 3 births, all right, because you have to have all 3. You can't break it down any more than that, okay? All right, so notice the difference between a simple event and an event. When they say 2 boys and 1 girl, they are not saying what order they're in, all right? So that could be the girl is the youngest, the girl is the middle, or the girl is the oldest. Those are all examples of 2 boys and 1 girl. So this is an event, but it's not a simple event, okay? Because there's more than one way that it can happen. Okay, so with 1 birth, the result of 1 girl is a simple event. The result of 1 boy is a simple event. Can't be broken down any further. I have a feeling that these remaining, you know, out of the 5 slides are going to be probably things you already heard me say. With 3 births, the result of 2 girls followed by a boy, in other words, girl, girl, boy, that's a simple event. Okay. When you roll a single die, some people don't know that the word die is singular for dice. All right, so we're talking dice. The outcome of 5, rolling a 5 on one die, that's a simple event. But the outcome of rolling an even number is not a simple event because that can be broken down into 2, 4, 6, right? There's 3 different ways that can happen. Okay, as we said before, with 3 births, the event of 2 girls and 1 boy is not a simple event because there are 3 different ways it can happen. You see them right there. Actually, I think earlier they had 2 boys and a girl, didn't they? All right, so they switched it up here, but it's the same idea. Okay, and then your sample space is the list of all possible things that can happen. So if you're only having 1 child, the possible results are boy or girl. That's all of them. But if you're having 3 kids, then there are all these different possibilities when you take into account, you know, the order of the births. Okay. All right. Little more notation. We use the letter P to stand for probability. We use capital letters like ABC to stand for events. So when you see something like this, that is read P of A, the probability of A. Okay. So it's not like P times A. P doesn't stand for a number. P is what we call a function. Okay. Probability of A. All right, I kind of like this little diagram here. So again, probabilities go from 0 to 1. Probability of 0 means the event is impossible, absolutely cannot happen. Probability of 1 means the event is certain, it is guaranteed to happen. Okay, but most of the time your probability is somewhere between 0 and 1. If it's 0.5, then that means 50-50 chance. It's just as likely to occur as not occur. When you get closer to 1, your event gets more likely. When you get closer to 0, your event gets more unlikely. Okay, so there are 3 different approaches for finding probability, and which one you use will kind of depend on what situation you're in, okay? But this is a fundamental rule of probability. If you're going to call something a probability, it absolutely has to be between 0 and 1. Okay? The number 2 cannot be called a probability. The number -1 cannot be called a probability. It has to be between 0 and 1. So the first approach is called the relative frequency approximation. So this is where you actually watch the procedure being done a whole bunch of times. So for example, let's say that I survey 1,000 families that have 3 children. And I asked them, what was the birth order of your children? Did you have 2 girls and then a boy? Did you have 3 boys? All right. And I actually counted those up. And so if I used that approach to say, find the probability of having 3 girls, you would just count how many of the families in your survey had 3 girls, divided by how many families did you ask. Okay, that's called the relative frequency approximation. Okay, so that's good for things that have already happened. All right, so you're not really trying to use it to make a prediction, but you're using it on something that actually has already occurred. Or when you don't know how to calculate it sort of more mathematically using a formula. Okay. The mathematical approach to calculating a probability is this one here. It's called the classical approach. Notice that it requires equally likely outcomes. If a procedure has n different simple events, different outcomes that are equally likely, and if the event A can occur in S different ways, Okay, then the classical probability would just be the number of ways A can occur divided by the total number of ways the thing can turn out. Okay? And then you just divide S by N. Okay. So just as a quick example, I might be stealing something I was planning to do later. In the one that we were just talking about, with looking at families that have 3 children, if I wanted to find the probability of having 2 girls and a boy, okay, remember that there were 8 different simple events in that sample space. Okay, so the classical probability for that event would be, it would have 8 on the bottom, and then there were 3 different ways that you could have 2 girls and a boy, right? You could have, your boy could be the youngest, like in my family, or your boy could be in the middle, or your boy could be the oldest. So the classical probability of having 2 girls and a boy would be 3/8, 3/8. Okay. That's an example of a classical approach to probability. Notice that, again, it requires that your outcomes are equally likely. Okay, so I am assuming that in this process of having 3 children, that any one of these outcomes or any one of the others are all equally likely. Okay. And then the last approach to probability is called subjective. So that's kind of where you guess. All right, if I get in this elevator, what's the probability I'm going to get stuck? All right, there's probably not a whole lot of data to help you figure that out, and I wouldn't have a clue how to figure that out, you know, with a formula. So that's when people say things like, you know, there's a 1 in a million chance I'm going to get stuck in this elevator. That's a subjective probability when people just guess. Okay, and then when all else fails, and we're not going to talk about this, this is the last section of chapter 4. Sometimes none of the preceding 3 approaches can be used. I was going to use this once for a problem that I found interesting, and then I just never got around to it. A simulation of a procedure is a process that behaves in the same way as the procedure itself. Computer program. You write a computer program that will randomly, you know, 3 times pick the letter G or B and then put them together. And you can tell a computer to do that 1,000,000 times, right? And it'll get it done in less than a second. And then you just ask the computer, how many of those 1,000,000 times did you get either this, this, or this? Okay. And I bet you would find that it's pretty close to this number. Okay. All right, let's see. Okay, when you express the value of a probability, you should either write it as an exact fraction or decimal, or round it off to 3 significant digits. So notice I didn't say 3 decimal places. The difference is that sometimes probabilities of unlikely events will start with a bunch of zeros. So when they say 3 significant digits, they mean like this. Okay. So keep going until you get to a number that's not a 0, and then put 3 more. Okay. When a probability is not a simple fraction like 2/3 or 5/9, in other words, I would probably never use a fraction like 374 over 1013, right? Yes, that's a perfectly good fraction, but you know, even I'm going to kind of stare at that and be like, okay, what is that as a percentage, right? They suggest that you write a fraction like this as a decimal instead, okay? Because it'll be easier to understand. I would say that would be a good idea if your fraction would have a denominator bigger than about, I'd say 12, all right? If when you put your fraction in lowest terms, if the denominator is bigger than about 12, you might want to think about writing it as a decimal instead. Okay. All right, so this kind of goes to what I said a minute ago about the simulation. If you wrote a computer program that 1,000,000 times would generate random sequences of B's and G's, 3 of them, and then I asked the computer, okay, how many of those 1,000,000 times was it 2 girls and a boy? And I said probably that proportion would be pretty close to 3/8. That is called the law of large numbers. When you repeat a procedure over and over again, the relative frequency probability gets very, very close to the classical probability, the one that comes from the mathematical formula. Okay, so that's kind of cool. Okay, but notice, in order for that to work, you really have to do a large number of trials. That's why I said like 1,000,000, all right? If you know nothing about the likelihood of different possible outcomes, you should not assume that they're equally likely, all right? And that's even people like me who have been doing probability for 1,000,000 years, we sometimes get tripped up by this. We assume things are equally likely that are not actually equally likely. There are a lot of really, really hard probability problems out there. All right, let's see. All right, well, we'll talk about this example real quick and then end this part of the video. So this is a very sort of open-ended question, and they really didn't give me a whole lot of data to figure it out. But then they go on to say, in a recent year, there were about 3,000,000 skydiving jumps, and only 21 of them resulted in deaths. So using the relative frequency approach, I would say that the probability of a skydiving jump resulting in death would be 21 over 3,000,000. This is a great example. They have too many zeros there, don't they? Okay. 21 out of 3,000,000. I would not leave that as a fraction. I would write that as a decimal, 0.000007. That's good enough for me. I'm not going skydiving, right? Okay. Can't use the classical approach because I don't know what the equally likely outcomes would be. Okay. Or you might just hear people say, oh, there's a 1 in 1,000,000 chance. All right. And what they're saying really is just that it's extremely, extremely unlikely.